Okay, we're going to talk about derivatives and numerical approximation of derivatives. So this chapter covers several things. I'm really going to focus on this one and a little bit of number 2. But mostly on this one because I want to show in Excel or in spreadsheet how the formula you use to approximate a derivative makes a big difference. There are bad formulas and good formulas. All right. The definition of derivative is here. This should be well known from calculus. So you can imagine that one way to approximate derivative is take a small value of delta x. Of course, this is the limit as delta x goes to 0. So if I take delta x very, very small, then I can evaluate f of x plus delta x and subtract f of x and divide by delta x and get a good close approximation to f prime. I want you to notice here that something that what you're doing is you're subtracting the difference of almost equal numbers. F of x plus delta x will be approximately equal to f of x if delta x is small. We saw already when we talked about propagation of errors that this is a dangerous thing to do when you're doing numerical computations. A small error in either one of these can lead to a huge error in the estimation of the derivative. So there are difficulties with estimating derivatives, no matter how you slice it. You need to have accurate function values to get good estimates of derivatives. All right. That's not the only way you could approximate derivative. Typically, you take delta x as positive. It would be just as good to take delta x as negative. All right, here's an example of the forward difference approximation to the derivative. I want to calculate the derivative x at this point. So I take here's the f of x here. I mean f of x is this level here. The level up here is f of x plus delta x. All right, let me back up a little bit. Let's just do it this way. All right, the f of x is here. This value is f of x. This value is f of x plus delta x. And you can see, if you think about it, that the formula f of x plus delta x minus f of x over delta x is just the slope of this secant line. Now notice there's a difference between the slope of this secant line and the tangent. The tangent is down here, the secant line is up there. So there's definitely an error, particularly when there's curvature in the function. In fact, you can relate the error in the derivative to the curvature of the function. Nonetheless, this does approximate to some degree this derivative, and if you take delta x smaller and smaller, you can see that the secant line becomes closer and closer to the tangent line. All right, here is an example done for this case. Now, it's also possible to do a backward difference. Essentially, you're taking delta x as negative. And that's the picture here. I'm trying to evaluate the derivative at this point. Remember, the derivative is the slope of this tangent line. And I'm approximating it by the slope of this secant line. All right. Now, if you'll notice something, when you had this positive curvature, this slope is certainly too small, and the other slope is certainly too big. Right? This slope of the secant line is bigger than the derivative. So what about if you take the average? Okay. What would the average look like? Well, he talks about that down here. When he talks about f of x plus delta, he's imagining dividing x up into Here we have x and x plus delta. Oh, I'm sorry. X plus delta. Another way of representing this, since I'm taking discrete values of x, and these values of x will have an index. Let's suppose this one is xi, and this is xi plus 1. And this would be xi minus 1. Okay. My index I can be arbitrary because I might take the derivative at any point along this line. If I'm looking for the derivative at this point, and this point x corresponds to xi, then I can write my derivatives in terms of these numbers. So if I have forward difference would be f of xi plus 1 minus f of xi over delta x. My backward difference would be f of xi minus f of xi minus 1 over delta x. And if I take the average of these two, you can work it out. You would get f of xi plus 1 minus f of xi minus 1 divided by 2 delta x. There's another name for this. It's called centered difference. Okay, it's called centered difference because I'm taking the function value at this point and at this point when I'm trying to evaluate the derivative of the function in the middle. And if you look at these pictures, centered difference looks like a pretty good idea. If you want the slope of this secant line, that's pretty close to the slope halfway between these 2 points. Right? If I take the point halfway in between, and I take the slope there, that's pretty close to the slope of this secant line. That means that it's a good idea to take the difference forward and backward and take the average. So what we're going to do is we're going to compare these three approximations. We're going to compare forward difference with backward difference and with center difference. Here's center difference here. Okay. And there's forward difference. I'm not sure where backward difference is, but I wrote the formulas up here. Forward difference, backward difference, center difference. So we'll compare the errors corresponding to those three schemes.